Find the depth of water, d, in meters. In this problem, a reservoir of water is held back by a gate. The depth of water in the reservoir is represented by the variable d, and the dimensions of the gate measure 5 meters by 3 meters. For this problem, we'll assume the mass of the gate equals 0. At the top end of the gate, a rope is attached and wraps around a pulley and connects to a mass, m. The value of this mass is provided, as well as the angles theta and phi, as shown on the diagram. The problem asks to find the depth of water, d, which we'll find by summing the moment around the hinge, which we'll call point A. The sum of the moments about point A equals the moment caused by the mass pulling the rope, mm, plus the moment caused by the water, mw. We'll first compute the moment from the mass, mm, which equals m times g times the height of the gate times the sine of angle phi. After plugging in these four variables, the moment caused by the mass equals 122,625 kilogram meters squared per second squared. This value is positive because we'll define the moment in the counterclockwise direction as positive. Next, we have to solve for the moment caused by the hydrostatic force of the water, mw. From observation, this moment will be negative and involve the variable d, the depth of water, which is what we're trying to solve for. The moment from the water equals Fw times Lc, where Fw represents the hydrostatic force caused by the water, and Lc represents the length along the gate from point A, the hinge, to the point on the gate corresponding to the centroid of the hydrostatic force. If we sketch out the profile of the hydrostatic force along the gate, we notice this force acts normal to the gate, and the magnitude of the force increases linearly with depth. We'll define the length of the submerged portion of the gate with the variable L, which makes the length LC equal to L divided by 3. And from trigonometry, we can equate the length L to the depth d divided by the sine of angle theta. After making the substitution for variable L, the variable LC equals d divided by 3 times the sine of theta. Next, we'll solve for the hydrostatic force caused by the water, Fw. The hydrostatic force equals rho times g times dc times A, where those four variables represent the density of the fluid, the gravitational acceleration, the depth of the centroid, and the area of the gate. Since the fluid behind the door is water, we'll use a density of 999 kilograms per meter cubed. And the gravitational acceleration, g, equals 9.81 meters per second squared. The depth of centroid, dc, equals half of the depth of water, d over 2. And the area of the gate, A, equals the width of the gate times the submerged length of the gate, L. From the problem statement, we know the width of the gate equals 3 meters, and we previously defined the value of L as the depth of water divided by the sine of angle theta. And the problem statement provides theta equals 60 degrees. Now, with all these variables, we'll write out a revised equation for the moment caused by the hydrostatic force of the water, mw, which equals 6,533 d cubed kilogram per meter second squared. Since this moment acts in the clockwise direction around point A, we'll add a negative sign in front, so it is negative 6,533 d cubed kilogram per meter second squared. Lastly, we can plug this value for variable mw into our equation, summing up the moments around point A. From there, we can solve for the value of d, which equals 2.66 meters. When reviewing the possible solutions, the answer is B.